In this video, I want to go through an example of testing the variation amongst two samples. Let's go ahead and take a look at an example. There are two Chevrolet dealers in Jamestown, New York. The mean monthly sales at Sharkey Chevy and David White Chevrolet are about the same. However, Tom Sharkey, the owner of Sharkey Chevy, believes his sales are more consistent. Below is the number of new cars sold at Sharkey in the last 7 months and for the last 8 of David White. Does the evidence support Mr. Sharkey's belief that his sales are more consistent? Use the significance level at 0.01. Okay, let's go ahead and open up the starting file. Okay, so there's a few points in this problem I want to talk about. We're basically testing the variation amongst these two samples, not the means. So the distribution that we're going to use is actually a little bit different. I'm going to talk about that in a little later. The first thing I want to point out is that we have this keyword of more consistent. In terms of variation, what does more consistent mean? Well, to me, more consistent means that your variance is lower. In other words, your standard deviation is lower. Variance is calculated based on the squaring the standard deviation. Okay, so in terms of writing an alternative hypothesis, what we can actually use is the same technique we've been using through our single and two sample hypothesis tests about the mean. So let's go ahead and document this. We have H0 and H1. We have the sigma, which is the variance. Well, before I actually do that, let's write it through the alternative. We have more consistent, so we know that'll be a less than. We have sigma Sharkey is less than, meaning it's more consistent than, sigma White. Okay, so again, I always like to write the alternative first and then go back and write the null. So we have sigma Sharkey is greater than or equal to sigma White. Of course, we can actually rewrite this in a slightly different manner. We could say, or we will write it this way. I'm just going to copy and paste these. And actually what I'm going to do, I'm going to subtract sigma White from both sides. So sigma White minus, so sigma Sharkey minus sigma White is greater than or equal to 0. And then down here, sigma Sharkey minus sigma White is less than 0. Okay, so very similar to what we've done before. Okay, so we can identify alpha in the problem. That's going to be 0.01. The test that we're going to run is no longer a T or a Z. T and Z's are for testing the mean. We're going to test the F. So once I finish this format, I want to talk about this F distribution a little bit. So let's open up our formula sheet. Underneath this section, analysis of variance, we have some notes essentially. The F distribution is used to test the hypothesis that the variance of one normal population or sample equals the variance of another normal population or sample. Okay, so what does the F look like? The Z and T that we're all accustomed to look like a normal distribution that's equally distributed in bell shape and symmetrical. The F distribution looks a little bit different. One reason being we can't have negative variation. Okay, so the distribution starts at 0. And when we're comparing two different samples, the distribution of this F distribution takes on a shape based on the degrees of freedom in both samples. One for the first sample and one for the second. Okay, so these are general representations of the F distribution based on a variety of degrees of freedom. Okay, so when we're writing out hypothesis statements, we've already written ours. And testing the variance is just slightly different because the way in which we calculate the F stat is based on the variation of S1, whatever we define as sample 1, over the variation of sample 2. Well, this poses a problem because we could have a situation where, let's say, the sample 1 in this situation has a higher variation. So let's call it 10 just for the example, where sample 2 has a variation of 1. If we do this, we're left with a value that's positive. In fact, it's a value greater than 1 in ratio. What if we have the other hand, though? What if we have S1 is 1 and S2, the variation, is 10? Then we have a fraction. Okay, so now it's going to be a fraction below 0. So there is a common practice when we're looking at the f-stats, and the common practice is to assign variable 1, S1, the sample with the highest variation. Now, we don't have to do that, and sometimes it can cause problems when we have a set way of looking at constructing the null and alternative hypothesis. And that's why I wanted to take a minute to review these notes. Okay, so we can always interpret the results based on the p-value, and that's what we're going to do. But I'm going to go ahead and show you through our demonstration what I'm talking about related to this F statistic. I have provided notes here about what to do when to reject the null under two circumstances. One, if you use the sample 1 variation is greater than sample 2 variation, we reject null if F stat is greater than F critical. Second situation, if what you're calling sample 1 has less of a standard variance than the variance of sample 2, then we have a different rule, and it's because of that fractional component here and the one or above here. So let's go ahead and take a look at the rules that we're going to use in terms of when we're going to reject. So essentially, this is what we have. This is based on the common usage where we're producing F statistics that are positive and they are above 1. We can use this as a general guide. When we have a critical value, it's going to define our critical range and our do not reject and our reject range. So let's go back to the problem. We've concluded that the test is going to use that F distribution. Let's do a little calculation here. We have the standard deviation, and we can calculate that, STDEV, based on the samples we were provided. And we've got to include this last one here. If we wanted to calculate variance, VAR, we could simply square these terms. And I'm going to provide some formatting. So we notice that we have, in effect, called sample 1 Sharky because we wanted to use the convention that we're used to using in terms of setting up the alternative hypothesis. However, it's a little confusing because here Sharky has the least amount of variation, which goes against the traditional wisdom. That's okay, but we just have to know that there is this issue so we can interpret the results correctly. And like I said, we can always use the p-value to make sure we're interpreting this hypothesis correctly. So let's go ahead and run the analysis. Okay, let's go to data, find the data analysis, go to the fstat2 sample for variances. I'm going to delete the previous information I had in this particular spreadsheet. And here I'm going to put Sharky as 1 based on our hypothesis. I'm going to put David White as variable 2. I have labels. My alpha is 0.01. And I'm going to put this report right here for now. Now I want you to look at this. Our variation is actually calculated the same, 218.81 and 526. Okay, that's fine. The point I'm trying to make is within this portion of the table. We have F stat at 0.4 and we have F critical at 0.1. Well, again, this is a sort of an awkward situation because we have put Sharkey with the lowest variation in the numerator and leaving David White in the denominator. So what I would recommend highly is, regardless of the order that you put your samples in, look at the p-value. The p-value is going to say the same thing if we interpret the F statistics and critical value correctly. The p-value is saying it's a very high value. It's larger than alpha, which means we failed to reject the null. So let's document that conclusion. Fail to reject null, which means that essentially Sharkey is as, let's see, how do we put this in terms of consistency, is just as, well, the main point is that there is no difference. Sharkey is not less. So Sharkey is not more consistent than White. Okay, so that's really our conclusion. At least we don't have enough evidence to support that particular claim. Okay, so I want to come full circle in this example, and I want to show you, if you change the order of presentation, how these values change. And again, you can always make a good decision based on the p-value, which is why so many software titles only show you the p-value. Let's go back to data analysis, leave it at F, and I'm just going to swap the order. So here, instead of having Sharkey as sample 1, I'm going to have David White. Go down to 2, instead of White, I'm going to have Sharkey. I'm going to place those results here. Now look what's happened here. We have the same statistics calculated. Of course, they're in a different row. But look at our F value. Our F value has changed. And it's because now S1, if you will, variation of 1 is now David White, which is 500. If we were to calculate this F stat manually, it's simply the ratio of David White's variation divided by Sharkey's. We get that 2.4. Okay, if we were to do that over here, and I'll just do it right here, we get this. So we're dividing 200 by divided by 526. So that's the reason why there's a difference. And in addition to that, that's why there's a difference in the F critical. Now, ignoring all that, we can make the same decision, because look at our p-values. Our p-values are identical. They are the same. So what I'm recommending is always look at your p-value. If your p-value is greater than alpha, we fail to reject our null. If p-value is lower than alpha, then we can reject the null.